Welcome back to ECE 320A. Homework number 5 is due this evening. If you haven't already turned that in or clicked the right buttons in mastering. Our next exam is on Thursday, the next time we meet in class. Today I will just quickly slide through the process. For exam number 2, we will take a quiz, the normal quizzes that we have in here for the final value theorem. We will look at some examples with the initial value theorem, and then we will hopefully get to this equivalence relationship that I keep referring to, and you've probably seen on all the practice exams. Where are these two sums of sines and cosines? Why are they always said equal to, or they're equivalent to, another expression that only has a cosine? And we'll try to illustrate how you can go or move back and forth between those, and then we will look at a circuit example and maybe get into, or at least motivate, whatever chapter we're going to, 13, the lucky chapter. Here's the exam number 2 process. You now get one additional sheet of notes, so when you're planning for exam 3, you'll have 3 sheets of notes. You have 4 pages, essentially, 8.5 by 11 inches, by doing the front and back of those 2. If you want to have Laplace transform tables, you need to put those on your sheet. Don't expect me to have those and give those to you, because you want to work with something you're familiar with. And if you've put them on your sheet yourself, you know where they are and what they mean. If I give you a table, you're going, I've never seen it that way before. It confused me. I don't want to confuse you on the exam, not with a table. Tables are designed to eat on or something. Yes? If the question was, if we're using the Laplace transform table, I think at this point, if it's in the table on a row of, let's say, table 12.1, I know where you're getting it. So if it's 1 over s and you say inverse Laplace is u of t, that's fine. I know that you are getting it. Or if you have e to the minus 6t, then you write down 1 over s plus 6. That's fine. You don't have to derive anything unless you need to show something that is a little bit outside of those table entries. Then you might have to start doing some derivation or some operations with the Laplace transforms, and that's table 12.2. Yes?
Would it be incorrect if when we inverse Laplace transform something and we get a delta function, would it be incorrect to multiply that by a unit step, the u of t?
So the question was, how can we just throw u of t's everywhere? No, that's not quite the question, but I rephrased it. If you have an impulse, you don't have to multiply it by the u of t. That impulse is kicking on right at 0, so don't worry about trying to turn it on or off with the unit step. That impulse is something that happens right at 0, and if you have delta of t by itself, that's fine. And how are you going to get delta of t by itself in the time domain? If you have just a number, a constant in your frequency domain expression. If you have a scaled s in your s domain sitting by itself, then what do you get in the time domain? A derivative, the scaled derivative of the impulse. And you should be comfortable with all of that. So there's the process for exam 2. I want to get quickly into our quiz. Here's our quiz. And this is to just get you ready for the exam 1 or 1 or 2 of the questions that might be there. How do I quickly assess whether or not I can apply the final value theorem or not? Here is part A. Can you apply the final value theorem to this transform? And if you said yes, why are you saying yes? You're looking at this expression, aren't you? S x sub a, and you're checking the poles of that expression. By including that s in this numerator, you haven't changed the denominator, and the denominator started with all of its roots in the left half plane. And so, yes, you can Fourier transform. You can do the final value theorem on capital X sub a. And what would the structure of your response be? What terms would you have? What modes would be there? An e to the minus t term and an e to the minus 3t term. And those would be only on for t greater than or equal to 0, or you could put the entire expression inside square brackets or parentheses and multiply by u of t, and that does the same switching. That's where your u of t is handy, coming into play. How about the Laplace, or the final value theorem for b? Is it applicable, or can you apply the final value theorem to capital X sub b? Yes. Here you're looking again at s times x sub b. Those s's cancel. And now we look at what's left in the denominator, and we evaluate that or set that equal to 0 and find the values of s that cause that to equal 0. In this case, you only have one remaining pole, and it's in the left half plane. You can apply the final value theorem to b. How about b prime? No. Now we have two poles sitting at the origin. And what would the structure of the time domain response look like here? If I said, what is little x sub b prime of t, what pieces would you have in your time domain expression? You would have a t, a constant, and a damped exponential, an e to the minus t. Does everybody see that structure? And that you had three terms, it's a third order. You're trying to have a way to check your work. Can you apply the final value theorem to c? Does anybody have a coin? I'm hearing some yeses and nos fairly equally. Which one is going to win out? No, nothing's going to win out, or no is going to win out. I don't know how to interpret that. If the answer is no, so if you, on the exam, if you say no, tell me why, okay? What's the reason this is a no? Whoa. We have poles on the imaginary axis, and those are not going to ever reach a final value. They just keep shaking. What's the frequency that they're shaking at? They're vertical, aren't they? They're right on the axis. No damping, no exponential growth. They're right there. And what do you want? When you're checking the poles, where do they have to not be? They can't be anywhere on the right-hand side or on the imaginary axis. What's the exception to that? In your original transform, you can have one, can't you? Pole at the origin. That one's okay. What about D? Is this one Laplace can you apply the final value theorem to this? What's the structure of the result for this example? Okay, so we've been seeing the hypotenuse before the first exam. Now what do we see on this problem? We have ones everywhere, don't we? But where is one of those ones going to appear? Okay, if you looked at this, so when you see this, do you physically see the x's in the s-plane? Do you see where they are located? Do you see poles at -1 plus and minus j1? I mean, I haven't done it, but I could do that and not change anything, right? So there's my omega. My omega, the rate that it's oscillating is 1 radian per second. The exponential decay is -1, or it's e to the minus t. So this is now shaking at 1 radian per second, but it's collapsing exponentially with this rate e to the minus t. And that's all a consequence of having poles at those two locations. And the further they are into the left half plane, the quicker it exponentially decays. The further away they are from the real axis, the faster it shakes, right? That's the bigger the omega. And so knowing where your poles are in the complex S-plane gives you a visual of how this response is behaving. Can we apply the final value theorem to E? How is it going to shake? Is it at all like any of the earlier examples? What's different between D and E? One is passing and one is failing. Sorry. Shouldn't go there. It's not the right frame of mind for an exam. D and E, are they at all alike? They have the same exact denominator. What does that mean? The poles are exactly the same. So you have an e to the minus t cosine of t, an e to the minus t sine of t, making up your response. The numerator, being different, changes those weights on those, or the coefficients that are in front of those terms, e to the minus t cosine of t and e to the minus t sine of t. Can you write down what little x of e of t is without getting out your calculator? Now I've schooled you to think in terms of complex, but we can actually solve this without doing complex arithmetic. The poles are complex, aren't they? They're at -1 plus and minus j1. But this is I can rewrite that as, what would the cosine in the frequency domain look like? If I had a cosine that had these poles, it's an exponentially damped cosine. Do you remember what the structure is for this in the table? And maybe it's not even in your table in the textbook. They kind of focus on the complex. What's the structure if this was the cosine piece? It has an s plus 1 up top. So we know we have some a amount of that. But we know that we don't have just a cosine because 4 is not equal to 7, is it? If 7 was 4, then we would have 4 of these cosine exponentially damped in the time domain. We don't have that. Generically, then, we have to say, well, we have b of the sine piece, and what's the sine piece look like? That's just omega, which in this case is 1. Now all we have to do is pick a and b so that we end up with a numerator of 4s plus 7. I can form a common denominator. I can put that numerator over the same denominator. It's exactly the same. I'm now saying that I'm wanting x sub e of s to be some a s plus 1 plus b over s plus 1 squared plus 1 squared. And now do you see what a has to be? A has to be 4. You do have 4 of these cosines terms. And then we can back out what b needs to be by equating the numerator. We now have 4s plus 7 is equal to as plus a plus b. The s coefficient, or equating coefficients there, we have 4 on the left and we have a on the right. There's our a. And if we look at the constants, or the s to the 0 coefficients, we have 7 on the left and we have a plus b. We just said, or just found, that a was 4. Whoops, what am I doing? So now what's b? Now I know why I'm questioning or scratching my head, is because my notes are not what I just wrote down. I was working another problem on my notes. Wake me up. All right, so now what do we have? We now have 4 s plus 1 over s plus 1 squared plus 1 squared plus 3 times 1 s plus 1 squared plus 1 squared. And now you don't have to say anything more. You can just say the inverse Laplace of that is 4 e to the minus t cosine of t plus 3 e to the minus t sine of t. This is not a very good example because I have 1's everywhere. I have 1 in the exponent, I have 1 in the omega location. But is it clear where that came from? Questions on the final value theorem. And we didn't have to get on our calculator and do complex algebra, did we? We just had to say, oh, this is some linear combination. Generically, if you see this, and the numerator is not just a constant, and it's not some multiple of the s plus a term, then you know you have a combination of exponentially damped sine and exponentially damped cosine. And that's why you can say, oh, the structure is this, and just write it down. Yes?
If the e to the minus t is that 1 from the s plus 1 squared? Or is that...
That's why I said this was not a very good example. The question was, where are all these 1's coming from? This 1 is sitting right there, and this 1, it's blue, is sitting right there. This 1 is sitting right here. This 1 is sitting right there. This 3 is right there, and this 4 is right there. And that's how we populated that time domain. Oh! T greater than or equal to 0. This is not happening for all time. We're doing the one-sided Laplace transform. Was that the question?
No, I just had a question. Is this the only time we're going to have both like a combination of cosine and sine?
No. So the question was, is this the only time that we would, well, I'm not, you'll learn not to say only and forever and all, especially in your, never mind. If you're in an argument, those are not words to use. You never, you always refrain from that. Speak. So, if you have something like alpha s plus, why am I using alphas? Because I use those all the time somewhere else. Let's say that I have gamma 1s plus gamma sub 2 over s plus alpha squared plus beta squared. Then automatically you can say, oh, my structure is a e to the minus alpha t cosine of beta t plus some b e to the minus alpha t sine of beta t, and that's for t greater than or equal to 0. Not knowing what gamma 1 and gamma 2 are, it immediately tells you that those will influence A and B, and unless they are some special relationship between gamma and 1 and gamma 2, you're always going to have an A and a B. They may be positive, they may be negative, but you always have this A and B if I just ask for the structure. Was that your question? We were talking about the final value theorem. Let's now go back the other direction and look at the initial value theorem. I think we only covered one last time in class, so let's look at, let's say, example 2. Suppose that I now have capital X sub s, s plus 1 over s, s plus 2. Can I apply the initial value theorem? There's really no question there. You just see if you can find a limit. In this case, you're saying x of 0 plus is equal to the limit as s goes where? This one now goes off to infinity of s capital X of s. What's the limit? It's 1, because I'm now really focusing on the leading coefficient. If I wanted to, if I didn't want to look at squares, I could actually cancel those, and now I have an s over an s, and those are dominating 1 and 2 in the numerator and denominator respectively. I end up with just a 1. What about the next example? Suppose that I said, can we apply the initial value theorem to capital Y of s, which is s over s squared plus 4? Do you see y of t, little y of t? Can you immediately write that down by looking at capital Y of s? If you can't, you need to be getting closer to doing that. Where are your poles? They're at plus and minus J2. This is oscillating, isn't it? Do you have any exponential decay on this? No. This is just a pure cosine or a sine. Is it a combination of sine and cosine? It's not, because we just have that isolated s term in the numerator. If we had something like s plus 6, then we have a combination of sine and cosine, both at the same frequency. The frequency is 2. In this case, if we just have, because we are starting just with an s, now we have just a pure cosine. Or depending on which way you prefer to write that, you can write it either way. They're equivalent. But you didn't have to do that. That was just sort of an aside. But you can now use that information to check your work if you now applied the initial value theorem. Where do you know you're starting if you look at little y of t at time 0? That should be 1. So now let's look at, whoops, this is y. This is why we do the initial value theorem. This is now the limit as s goes to infinity of s y of s and that's equal to 1. Questions on those examples or the way to apply the initial value theorem? The initial value theorem is not as constrained to apply as the final value theorem. Final value theorem, you have to check some things. And what you're checking is, are all of my poles in the left half plane? Let's now play a little bit with this idea of when we have complex roots or poles, and only use real numbers to, let's say, find the inverse Laplace transform. Suppose we are given f of s equal to 5s plus 2 over s plus 2 squared plus 3 squared. And on the exam, you might be asked, what is f of t? And that would actually be a gift, I think, at this stage. What are you now starting to ask yourself? Is it a cosine, is it a sine, or is it both? Generically, what do you know it's going to be? Both. Generically, it's always both. So if I ask you the structure without finding the coefficients, you're just going to include both terms. To write that down, then you need to know what values of s cause that to become 0, and the way that it's written, it immediately tells you that those poles are at minus 2 plus and minus j3. Now that you know the poles are there, you can immediately write down the structure of f of t. You could say, oh, that's some combination of a cosine that's exponentially damped and a sine that's exponentially damped. Or you could say, oh, well, I like to think of it as this one is nice to immediately write down from inspection of the poles, but to visualize that in your head, how do you combine these exponentially damped sines and cosines? That gets a little messy. That's why this expression with just a gain, k, e to the minus 2t cosine of 3t plus some angle, is maybe easier or cleaner to think about. Because now you simply have to shift the place where that cosine waveform peaks. But now you just have to worry about one cosine and not a cosine and a sine and adding those up point for point. Question?
So are we allowed to use like any one of those interchangeably?
Yes. So the question was, can we use either of these interchangeably? And the answer is yes. If I ask for the structure, either the top row is correct or the bottom row is correct. They're both correct. Yes.
When you write K, are you incorporating the magnitude of K times 2?
So this is maybe a poor choice for this coefficient because the book uses K there. So let me call it something else. Let me call this C. I was going to use C, but then I thought maybe that will make you think it's a cosine. C is just a constant. And K was just a constant. It wasn't the complex number that the book is using when it finds the complex partial fraction expansion coefficient K. Now, if this is the case, if this is capital F of S, maybe I'm asking for more than just the structure. I want to know what is little f of t. Now you could say, let me find or let me evaluate A and B. F of S was 5s plus 2. I know there's going to be a cosine piece and a sine piece. The cosine piece looks like what? I'll do the hard part. The denominator. So what's the numerator look like? It now is some a, s plus 2. Then I have the sine exponentially damped sine piece. Again, the denominator is exactly the denominator that I had in the cosine, but now what's the numerator here? B3. Bingo. Nobody plays bingo. Sorry. Here is the cosine piece. I meant to change colors, and now I have to erase every one of those dashes. Ugh. Hey, it's harder than it looks. I meant to go red. So there's the cosine. I think it'd miss more than one. Probably lose 19 points out of 20 on that, without that square there. There's the cosine piece right here, and here is the sine piece. And we're just saying we want to find what fraction of each of those we have. And we can find that by just equating the numerator on the left with the numerator on the right. On the left, we have 5s plus 2. On the right, we have as plus 2a plus 3b. And if we look at the coefficients of the linear term in S, we can see that immediately we found A. And if we look at our constants, we now find that we have B equal to minus 8 over 3. And we can now write down f of t. F of t is now 5 e to the minus 2t cosine 3t minus 8/3 e to the minus 2t sine of 3t.
If we write it in this, where we get the cosine and sine term, we'll never have theta term inside.
So now if we keep these two components, cosine and sine are actually orthogonal, aren't they? If we just write it in terms of exponentially damped cosines and exponentially damped sines, we won't have an angle in the arguments of those sine and cosine. This one's clean to write down. It's maybe not so clean to visualize what's going on because now you have to sketch two of these exponentially damped sines and cosines and add them up at each point in time t. And now you're going, but that's not what Jimmy got. Jimmy got a cosine, and only a cosine. And it had a theta. So where did that come from? How come somebody else has just a cosine? Because their mom or dad got them a nice calculator, right, that does the complex algebra, the complex math, and now they always want to use the complex numbers. Then what do we do? Now we have f of s is equal to 5s plus 2 over s plus 2 squared plus 3 squared is equal to, how many terms do I have on the right? 2. What's in the denominator? And what's in the numerator? Can I use k's? Since the book likes k's. So is k here? Is it? What did we talk about last night? It goes with this one. Why? This one has, where's the s that causes this to become 0? It's in the second quadrant, isn't it? That's the one we need to use with k. The other one is the conjugate of k. Is that clear? Otherwise, you're going to have a sign error, S-I-G-N error, in your answer, in the argument for theta. And now let's just solve for K1. What do we need to multiply by? And what do we, that's capital F of S, which give, and then we're evaluating where? Are you connecting all of these dots? Now, what is this expression actually going to be? I'll do the hard part. The numerator, what's downstairs? We've already canceled that s plus 2 minus j3 factor, so what's left is the j plus j3, and we're evaluating it at s equal to minus 2 plus j3. And if you do that, you end up with 5 halves plus j 4/3, if you do the complex math. And that's now K1. And to use the formulas, we need to write that rectangular form of the complex number in polar form. which means that we need to take the square of 2.5 and the square of 4/3, add them together and take the square root, and we end up with 16 or 17 over 6. And the angle on that K1 is the inverse tangent of the imaginary component over the real component of that complex number. And if we do all of that, 17 is not quite 18. If it was, it would be 3, so it's a little less than 3. Yes?
How do we get 5/2 plus j 4/3?
I don't know, magic. Question was, where did we get 5/2 and j 4/3? I'm just plugging in that particular value for s, which is minus 2 plus j3. What do I have in the denominator? j6 or 6j, and then in the numerator I'm going to have some minus 8 plus j15 if I'm doing the algebra right. And if you simplify that, you end up, I hope, with 2.5 plus j 1 1/3. That's where that came from. If you end up with a 0 denominator, then you know you were evaluating at the wrong value of s, or you canceled things wrong when you were doing it. Here, let's just say that this is now 2.833. We're doing mastering, so I needed 4 digits. And then my angle is 28 degrees. We typically think a little bit cleaner in degrees than we do in radians. But what's a radian? How many degrees? 180 over pi, right? And what's pi? A little bit bigger than 3, but 180 divided by 3 is 60 degrees, so it's a little less than 60 is 1 radian. 57 point something, 29, 57.3, I think. All right, where were we? Oh, now we need to find f of t. What is this? Can I write it down now that I found K1, or do I need to find K1 star? You have K1 star, don't I? It's just the conjugate of K1. What is little f of t? Why do you have that 2? Yeah, it's Euler, isn't it? It's that Euler relationship. So there's the 2. Then we have the magnitude of K1, which is 2.88. E to the minus, where were we? 2. Cosine of 3t. And this is just the angle of K1. And this becomes 2.833. And that's true for t greater than or equal to 0. And if we combine these, or if we scaled 2.8 by 2, we end up with 5.67. And this f of t and that f of t are exactly the same. They're equivalent. And now we put on our 2-year-old cap. And we say, why? Why are these two expressions equivalent? And we're going to have to do some age progression pretty quick because we're going to have to go from 2 in age to trig. Trigonometry. So maybe we go to preschool at 4 and get the trig. Question?
Is there ever a time where, like this method, or
Is there ever? Go ahead.
Okay, no, I'm saying is like, all right. So is there ever a time where like the cosine and the sine versus like this there anything where like one might be better than one?
You're making me make that judgment call better than the other?
Well,
No.
there's a time where you can't use
No. You should be fine to use either one. They are equivalent. It's just what I was suggesting is if you had to sketch this waveform mentally in your head, can you see that response a little bit cleaner than if you said, what's this look like in the time domain? Now you don't have to have two exponentially damped sines and cosines and adding those up mentally. Here you have the exponential envelope of decay, e to the minus sigma, and you know how fast you're shaking. With the omega, you just have to figure out what that theta is doing with the shifting of that waveform. But you only have one waveform. In terms of visualizing, I think this one's easier. Sometimes in terms of finding the answer, this one might be easier. Or just stating the structure, this one might be easier, saying, oh, I have sines and cosines. Now we need to get to trig. From 2 to trig. T. We're stuck on T. Tharp's doing 2. Sorry. So now what do we have? Well, if we're doing trig, we're actually using the cosine of A plus B, the sum of angles formula. And we're going to only do that. So we now have cosine omega t. You remember what this is? It's in the appendix of your book. And if you need that, you could put it on your crib sheet. Just saying. Not sure you need to prove this, but once you've seen it, you know how to do it, right? Is everybody comfortable with that? Now let's push that r inside and just keep the exponential decay out front. And let's put the cosine omega and the sine omega on the far right of those two expressions so that I now have r cosine of theta times the cosine of omega t. And then I have a minus r sine of theta times the sine of omega t. And now what I want to do is I want to say, let me call this, oh, now I know that my notation is probably going to confuse you. So let's call this A and this B. So that now we have e to the minus sigma t, A, I don't like that, but well, because now you're going to think it's arc cosine. Help me. I'm suffering up here. So can I call this alpha bar and beta bar without you getting mixed up with that being the e to the minus alpha t at some point? This is now alpha bar cosine omega t plus beta bar sine omega t. You guys are more comfortable with bars anyway. Sorry. Yeah, you have. I'm just checking to make sure you're awake. Where were we? Alpha bar. So what is alpha bar? Alpha bar is now r cosine of theta. It's homecoming. And beta bar is r minus r sine of theta. And that's after Thursday that you need to really worry about homecoming, right? Thursday is your exam. And after all of your exams, we are engineers, right? Have to study before we worry about other things. All right. Now, let's look at what happens if we take alpha and square it and add that to beta and square it. Then we have r squared cosine squared of theta plus r squared sine squared of theta. And now we see another trig identity, don't we? If we factor out the r squared, we have cosine squared plus sine squared, which is 1. And you've heard that joke, haven't you? Never mind. I don't. It's the MIT joke, so don't be offended by this. There was a gentleman at MIT, and he walked up to a lady that was sitting on the bench, and he goes, "You must be sine squared." And she goes, "What?" He goes, "Well, you must be sine squared, because I'm cosine squared, and together we're 1. I gave you the origin of that joke, okay? What is R? Stick to the script, Thorpe. Stick to the script. R is now just the square root of alpha bar squared plus beta bar squared. So now if you know your alpha bar and beta bar in this one way of writing it, you can get the magnitude piece, the R piece, by just taking the square root of the sum of the squares. And we can get the angle if we look at the ratio of beta bar over alpha bar. Beta bar was this minus r sine of theta, and alpha bar was r cosine of theta. The r's cancel and sine, so now I have minus sine theta over cosine theta, which is just minus tangent of theta. We can solve for theta, and now we have theta is the inverse tangent of minus beta bar over alpha bar. In our example, what did we have? We had alpha was 5, and beta, well, alpha bar was 5, and beta bar was that was the minus 8/3, wasn't it? So that now if we plug that in, we find that R better be a little bit bigger than 5. R is the square root of 5 squared plus 2 2/3 squared, which is 5.67, and theta is now the inverse tangent of minus a minus 8/3 over 5, or 8 over 15, which is 28.07 degrees. So now you know how to connect these two expressions. If you found the one with the alpha bar and the beta bar, you can immediately write that as one cosine with a phase shift. If you want to do this graphically, I sort of like this technique because it's visual.
Seems like it's faster just to do it out instead of doing all the tricks.
You just burst my bubble. It's kind of fun, isn't it? Not really? Oh, man. Sometimes you don't have to tell the truth. Here's the graphical way, and it's maybe quicker. So let's say you had alpha and beta, or alpha bar and beta bar. This is now the cosine direction, the positive cosine direction, or what we were saying is the alpha bar. And we had 5, didn't we, for our alpha bar, so it's right there. And the sine direction is 90 degrees behind the cosine. The positive sine direction is down here. And this was our beta bar. And what was our beta bar? It was minus 8/3, so we have to go up to right there. And now we just combine those. This length is r, and this angle is our theta. So if you now just find, you have this right triangle, it has sides of 5 and 8/3. You can find the hypotenuse, and you can find the angle of that triangle by taking the inverse tangent of minus beta bar over alpha. And you could get the same number, r and theta. You don't have to do any of this right here anymore, unless you want to. Now you know the relationship. And you can convert between, but what I'm really wanting you to be comfortable with is their equivalence and knowing that you can make that connection and how they are related, and you could quickly sketch those graphically if somebody gave it to you in the rectangular form, or if they gave it to you in the polar form, you could sketch this, and now you could say, oh, you want this in terms of cosine and sine, I can break it down into those rectangular pieces. Questions on that? So now, if you think of the sine waveform and the cosine waveform, what do you have in terms of a relationship? If I said something like sine of x, how do I write that in terms of cosine? Is this right? Is it the other way? So now if sine of 90 degrees is what? 1. Cosine of 0 is 1. So now if I drew x here, or theta there, then am I okay? Maybe I should have done it the other way in terms of cosine, but I'm pretty sure you can, essentially, if you now take the cosine of that angle, or if you looked at subtracting 90 from that angle and taking the sine, you will get the same answer. And this one, I could check that. Is that right? Actually, yeah. So that this is 0, and what's this? All right. So, that's how you have this. If you have a negative beta bar, you're actually going in the positive sort of y direction in this graph, and that will give you the angle that you need for theta. Let's look at a circuit. Suppose I give you the following circuit. V sub I of t, R, and C. Now, if somebody gave you that circuit on an interview, what would you tell them? It's a low-pass filter. And now they're going to say, well, can you demonstrate, or convince me of that? Or they might say, can you write the governing differential equation for that circuit? I'm sure they'll ask you that. No, you just tell them that. You say, oh, would you like me to give you the governing differential equation for that circuit? Hire this student. Right? How would you like to solve this circuit? I don't even think you need to tell me. I know how you're going to want to solve this. It's KVL, right? Which is fine. So let's now say that we have this current I. You're making me sorry I ever talked about a ladder. I think I'm going to go buy a ladder and bring it and carry it to class. I feel like that's now what I have to carry. Instead of a backpack, I'll just strap a ladder on. Can I do ladder analysis? Yes, go in the corner and do that ladder analysis. The circuit is up there in the corner. Start working. All right, so now we're doing our KVL. Minus V sub I of t plus R times I of t plus, should I call that VO or V sub C? I'm going to probably go back to V sub C. Can I change that to V sub C? Not allowed? I just made a ruling because I'm worrying about the governing differential equation. I became the governor. All right. Now what? How big or what size of a differential equation are you expecting out of that low-pass filter, the one that's on the board? Pardon? First order. We're expecting one derivative in this equation. Do we have a derivative yet in that equation? Where is it? It's in that I, isn't it? It's in ice. It's cold. It's the end of October. It's getting close to capacity. Ice. Ice tells us that we now have I sub C is C dV sub C dt. And this I sub C is the same as what we've called I in our circuit. So that now if we replace I with that derivative or differential expression or the current voltage relationship of that capacitor, and it's a derivative or differential relationship, we now have the source plus RC dV sub C dt plus V sub C of t is equal to 0. And if I only ask for the governing differential equation, you could stop there. But if I ask for V sub C of t, then you need to keep going. And maybe you've forgotten your differential equation, so now you go, I'm going to do Laplace. If we Laplace transform that, how do I Laplace transform little v sub I of t? This is the easy one, isn't it? Since I haven't told you yet what that voltage is, you can only assume that it's going to be something that can be Laplace transformed. And so I'm just going to make that a capital V sub I of s. What happens when I Laplace transform a derivative? Now I have an S, V sub C of S. And now what? I need to worry about my initial condition, which is minus V sub C of 0 minus. And both of those terms get scaled by the factor RC, plus the Laplace transform of little v sub c of t, and that's just capital V sub c of s. Yes?
If you don't tell us the initial conditions, do we not assume that there are not zero initial conditions?
Oh boy. If I don't give you an initial condition, you need to... You can tell me, you can say, since the initial conditions were not given, I will assume they were 0. But I might give you the initial condition, and then you would have to substitute it in. If I say in the problem statement, assume 0 initial conditions, you wouldn't have even had to include that term in this Laplace transform. You could have just assumed that. All right. So let's do that. Yes?
Let's assume T naught is not 0, it was like 2, but then you then have like V sub I of S minus 2, something like that.
Where's T naught?
Or there's a switch.
Oh, so now if there was a switch, you would have to worry about when this switch was opening and closing, and you would have to determine at what time are my initial conditions. Typically, we will have our switches being opened or closed at time 0. Except on some problems that might not be starting as circuits, they may be differential equations that now have some delays in them. Then you have to incorporate the appropriate shifting in the Laplace transform. Now that I have 0 for that constant, little v sub c of 0 minus, I can combine my terms that have capital V sub c of s, and I have s RC plus 1 v sub c of s is equal to v sub I of s. And now what we will do in the future is we want a transfer function. We maybe haven't talked about a transfer function yet. Maybe we have. But now we take the output, which was our capacitor voltage, the Laplace transform of that, and put that over the Laplace transform of our input, and now that gives us 1 over SRC plus 1. I've just done some algebra, that's all. And this we will call capital H of S, our transfer function. This piece in the red square bracket is the transfer function, and it's between the input signal and the output signal. Where the input signal is right there, and the output signal is right there. So I'm taking the output over the input to obtain my transfer function that gives me the transfer function between the input signal and the output. So if I multiplied this through by the input signal, I now have an expression that says, oh, the capacitor voltage's Laplace transform is now the transfer function times the Laplace transform of the input. And now somebody could start giving you different inputs, and you could start answering the question, what's the output going to look like for those different inputs? My system hasn't changed. My system is still this low-pass filter. It's still capital H of S. And now they can go and say, oh, make V sub I a step, make it a sine, make it an exponentially damped cosine. You can now Laplace transform all of those and put those in for the appropriate capital V sub I. Let's keep going. Suppose that somebody tells you that RC is 1/10. What is RC? It's our time constant, isn't it? RC is multiplying S, and S is a frequency. RC is a time. So now we have our time constant. And so when is infinity in this particular RC circuit? How long do you have to wait before you've reached a steady state if you hit this with a constant waveform? Or if you hit it with a sinusoid, how long will it take for the transients to be gone? Half of a second, 5 of those time constants. H of S now is 1 over RC, which is 1/10 S plus 1. And we can write this many different ways. If I factor out that 1/10 from both terms, and now put that 1/10 upstairs, I have two different ways of writing the same equivalent transfer function. This structure is called the time constant form because the time constant is scaling the leading power of S. This transfer function is called the pole zero form. Because in the pole zero form, can you immediately read off where the poles and the zeros are? They're not as directly visible in the time constant form, but they're still there. In the time constant form, it's pretty easy to see what the time constant is. It's 1/10. And in the pole zero form, where's your pole? At -10. In terms of a review for the exam, I already answered this question for the first part. Pole and zeros. Where are zeros in this low-pass filter? There are no finite values of S that cause that capital H of S to vanish, and we have one pole at -10. Now we can proceed to evaluate the behavior of this low-pass filter for different types of inputs. Behavior of circuit, to different inputs. Suppose that I had a constant input. In this case, my V sub I of t, let's say that somebody says, well, make that be 5 for all non-negative values of time. What's another way of writing little v sub I of t in terms of standard waveforms? Hint, hint. 5u of t. And now do you see what capital V sub I of S equals? 5 over S. Now we know what our V naught expression is. That's now this H of S times V sub I of S. For this particular V sub I, it's 10 over S plus 10, 5 over S. And do you now see the structure of the time domain waveform for V sub 0 of S? What's the partial fraction expansion of capital V sub 0 of S? What are the terms? How about if I switch them around on you? Does everybody see that? Now what's A? As a review, you should be able to just do this in your sleep. When you wake up tonight, tomorrow night, you roll over and you go, A, it's equal to S times V sub 0 of S evaluated at S equal to 0, right? So this now becomes 50 over S plus 10 evaluated at 0, or 5. What's B? B is 50, S evaluated at S equal to minus 10, minus 5. So that now we know exactly what V sub 0 of t is. It's 5 minus 5 e to the minus 10t, t greater than or equal to 0. And that was for a constant input. What's your final value? 5. You could do that from this time domain waveform, or you could do it from capital V sub 0 of S. I'll see you Thursday. Good luck. Homework is due tonight.